time?
Yep.
That's impressive.
We've got the best technology and the best people, right? Okay, so we're sharing the application. We are recording.
Do you want my biography, by the way? I printed it out.
You'd emailed it to me, so I got it on my,
You got
my
it.
phone. Okay. So I'll introduce you, and then we can just get started.
I don't know if you saw the message she popped up. She said you needed to sign her closed caption, right?
Oh, sorry. Yeah. Thank you. All right. Okay. Is that good? Okay. All right. I think the captionist is happy, so I think we can get started. If she's happy, then we're ready to go. Okay. First off, I want to thank everybody for coming. This is the first seminar of the 2019 session, and so hope everybody is going to enjoy this. Our speaker today is Robert Kleinberg. I met him at the Texas section of the APS meeting we had just last fall in October at University of Houston. And he is basically the Distinguished American Physical Society Lecturer. The American Physical Society flew him out here to talk to you guys as part of his speaking tour. A little bit about him. He has an undergraduate degree in chemistry from the University of California, Berkeley. And at the University of California, San Diego, he got a PhD in physics. He studied various properties of superfluid phases of liquid helium-3 in the laboratory of John C. Wheatley. From 80 until 2018, he was employed by Schlumberger, where his work focused on geophysical measurements. His current work at Columbia University and Boston University centers on energy, technology, and economics, and on environmental issues connected with oil and gas development. Dr. Kleinberg has authored more than 100 academic and professional papers, holds 39 U.S. patents, and is the inventor of several geophysical instruments that have been commercialized on a worldwide basis. Dr. Kleinberg is a member of the National Academy of Engineering and the 2018-2019 American Physical Society Distinguished Lecturer on Application of Physics. And that's why he is here today. So with that, I'll turn it over to Dr. Kleinberg. Okay. You're going to be in the control of the PowerPoint?
The usual buttons.
Yeah, usual buttons.
Okay.
If you need any help, let me know.
Okay. Well, good evening. Seminar at 7 o'clock. I really admire your fortitude. I don't know what time you got up this morning, but it's already a long day. So I am your American Physical Society Distinguished Lecturer on the Applications of Physics, as you've heard from David. Thank you for the introduction. And what this means is that I'm sort of going around the country basically talking about how physics students like you can make a transition from the academic world to sort of the real world of industrial applications and so on. And I think the society realized that there were really very few mentors for physics students. I mean, we talk about lack of mentors for women and minorities and so on, but really I think probably most people don't have mentors really in the sense that probably every physicist you know is in the university. You probably know very few outside. So this is an attempt to at least give you a little bit of a flavor of how at least one person made that transition. And later on we can talk about in more general details how you might make it. So the title, as you see, is MK to KM, how Millikelvin physics is used and reused to explore the Earth kilometers below the surface. So what you're going to see here is, as the slide says, a fully worked out example of how one physicist made the transition from pretty esoteric laboratory science to very practical real-world inventions. By the end of this talk, you'll have learned how to measure which way the wind was blowing 10 million years ago, and how to measure the sizes of pores in sedimentary rock and why those things are important. You'll also get a lesson in corporate jujitsu. It comes about halfway through the talk. I'd recommend that you do stay awake, at least until then, because that's the most important slide in the talk. Your experiences, those of you who make this transition from the academic world to the industrial world, will be different than mine, but I adapted to my time and place, and you will adapt to yours. So this is where it starts. This is a scene from my graduate school laboratory at the University of California in San Diego. The picture was published in 1976 in Physics Today. I'm sitting second from the right. I seem to be lecturing my much more learned colleague Matti Crusius on some fine point of physics. This was a lab where we studied superfluid phases of helium-3 shortly after they were discovered in the early 70s. And this picture is probably familiar to many of you, this sort of picture. And I must say, you know, at the time I had no inkling that I'd eventually wind up designing geophysical instrumentation. That's not why I went to graduate school. I went to graduate school probably for the same reason that many of you are studying physics, just out of sheer curiosity and love of the subject. But then the real world does intrude eventually. So as you heard, I went into the oil industry, Schlumberger, pronounced in the Texas fashion by our host, Professor Garrison. And so you might wonder how I got there and why. Well, in the 1970s, when I was in graduate school, the big pressing societal issue was the fact that oil-producing countries had embargoed the United States and cut off our supply of oil at a time when we no longer produced enough to satisfy our own needs. That led to lines at gasoline stations stretching around the block, and this was traumatic. This is, believe me, this was a traumatic experience for the country. And at the time, we weren't thinking of climate change, that climate science was still really in its infancy, and we weren't thinking about renewables, which at that time hadn't gained the efficiency and cost effectiveness they have today. So really, there was a general universal feeling that the only way to secure our economic security and independence from rival nations was to increase our supply of petroleum, of oil and gas. So that was the pressing national need that I was responding to when I left school. Sort of another of my influences was the fact I was living in San Diego, where there's the Scripps Institution of Oceanography. Several of my graduate school housemates were Scripps graduate students, and they sort of excited me about geology and, you know, plate tectonics and so on. It seemed like a really interesting subject, and so those two things came together, and I worked for Exxon for a couple of years in New Jersey. That was a postdoc. At the end of the two-year postdoc, I was once again on the job market, and there was this company, Schlumberger. Maybe you've seen the blue trucks rumbling around the roads here in Texas. I didn't know much about it at the time, but I did know that they were involved in the petroleum industry and geoscience and instrumentation. Schlumberger is really an instrumentation company, not a geology company. And of course, I had that graduate school experience in the lab, and there's the old Tektronix oscilloscope shown in the slide. So all those things sort of came together in what for me was a very fortunate coincidence of influences. So let's get into the sort of the meat of the talk. And the question I'm going to pose is, which way was the wind blowing 10 million years ago? And you might think, this is a ridiculous question. I mean, the wind is inherently ephemeral. Once it stops blowing, it stopped. I mean, what kind of evidence does it leave? And we'll get to that in a bit. But first, to get there, let's ask a simpler and sort of more direct question, which is, once you've drilled a well that produces water, where do you drill the next well? And to understand the context of that question, I have this little cartoon. This is a typical oil reservoir. I think this may be the only campus in Texas. You don't have a petroleum engineering department here in Clear Lake, do you? No. You may be the only school in Texas that doesn't have a petroleum engineering department. So I'll give you a really quick lesson on petroleum geology. So basically, oil and gas is formed deep within the earth when organic matter is broken down by high temperatures. And then because oil and gas is buoyant in water, and water is ubiquitous in the subsurface, the oil and gas slowly migrates upwards. And in many cases, it reaches the surface, which could either be the seabed or the land surface, and is oxidized in the ocean or atmosphere. But sometimes it encounters a layer that's called cap rock. It's sort of that blue-gray rock at the top, and that cap rock has the property that its permeability to fluid flow is very low. In other words, gas and oil can't get through it. It's kind of like cement. And so it's trapped, and if there's a dome-like structure, it'll be trapped underneath the dome, and that's all good. Now, because oil and gas is buoyant, it will float on water, so gas above oil, above water, like a jar of salad dressing. And if you drill into water and you hope that there might be oil and gas nearby, water's worthless to you because at depth it's both highly saline and somewhat radioactive, and it's just really toxic waste. But you really want to find the oil and gas that you need to power your economy. So the trick is you want to drill a well that's toward the top of the structure, toward the underneath the dome. So you can do that if you know which way the rock strata is sloping underneath the earth. Now there's usually no surface manifestation, but you've got an 8-inch borehole that's going through this rock layer. And the question is, from that 8-inch borehole, can you determine which way the rocks are sloping so that you can drill what the geologists call up dip, which is, in other words, toward the top of the dome. So how do we do that? That is the problem I was presented with during one phase of my career. Now, making measurements in borehole is really quite different than making measurements in your physics lab. So in the physics lab, the normal procedure is you've got your machine, and then you put the sample inside the machine. All good. In this case, we're putting the machine inside the sample, which is in fact the earth. So whatever you do, it has to fit inside a 4-inch steel tube. You can make it as long as you like because wells are very, very deep. They're typically kilometers deep, so you can have long equipment, but it's got to be very slender. So think long, skinny circuit boards. And inside that tube, you can put any combination of signal generators, voltmeters, whatever you want, but it's got to be inside. And then the whole thing goes into a 20-centimeter, 8-inch borehole into the earth. So that's the basic rule of the game. But there are more rules. And this is daunting, and especially for someone coming from the laboratory world, where you have kind of more control over your environment. In the earth, you don't really have much control over your environment. You have to take what it dishes out. So among other things, the apparatus, whatever you build, has to operate after being transported in Arctic, tropical, desert, or marine environments. It will probably be subjected to a 100 G shock at some point when somebody drops it. And then the thing is going to be dragged through kilometers of rough rock borehole. Now, the apparatus must operate while being exposed to temperatures ranging from minus 25 degrees C in the Arctic to 175 degrees C at the bottom of deep wells, because the earth gets hotter as you get deeper, and these wells can be 10 kilometers or 6 miles deep. It's going to be in a salt-saturated water environment, which is difficult, with pressures up to 140 megapascal or about 20,000 psi. You will be moving at least 15 centimeters a second because the clients are very impatient and don't want you, wasting time making your measurements while they're spending somewhere between $10,000 and $100,000 a day to rent the drilling rig that you're using. And so because you are moving in a hot environment, your temperature conditions are going to be changing continuously. So just think about your physics experiment and how would you like your temperature conditions to be changing continuously in the 175-degree centigrade range, far above military specifications. The apparatus must operate at the end of 10 kilometers of multi-conductor cable and autonomously and simultaneously with other nuclear, electromagnetic, and acoustic instruments, because we screw all these measurements together. It's sent down. The field engineer is a young guy, typically a graduate engineer or physicist. And he's got a lot of stuff to take care of all simultaneously, and he can't be fussing around with your particular instrument. So it has to be really very much autonomous. So looking at these specifications, I'm thinking, I'm a low temperature physicist. What the heck am I doing here? And then, of course, the initial panic does subside. And you think, okay, what am I going to do? This is not like helium. Those days are over. So, we all have a toolbox of things that we learned in school and experiences we had. So I thought back to an experiment I did with helium. It's shown here. This is a heat flow measurement. It's published in the Journal of Low Temperature Physics. I'm not going to explain this whole apparatus, don't worry. The only part that we're really interested in is the sort of blow-up part, which is circled with the red oval. And that is a mutual inductance coil set with a primary coil energized by a signal generator, as shown in the lower left of the slide. And there's balanced secondaries, so you have two secondary coils which are wound opposite to each other, so that if there's no sample in them, you have zero mutual inductance, or in other words, zero voltage at the output when you put in a current on the input. So a sample will unbalance.
Hold on a second. I want to check something with the settings here.
Because there's a little bit of sound coming back.
Well, yeah, that's me, but I think I need to, for the sharing, it wasn't advancing. So we have to just share the entire screen. Okay, oops. All right. Okay.
Should be good. Okay, now are we good? Okay. Well, I hope who's ever watching didn't miss all that stuff. So basically, this gets unbalanced when you put a sample in one leg of the secondary. In other words, that lower secondary, that unbalances it. Now you get a voltage when you turn on your signal generator. And the sample that we used was a paramagnetic salt, cerium magnesium nitrate. The magnetic susceptibility obeys the Curie-Weiss law, which is shown in the lower corner of the slide. So basically, it connects magnetic susceptibility, which is what you're measuring with this gizmo, with absolute temperature, T, with two calibration constants, which are, as we say, trivial to determine. Not necessarily easy, but trivial. So I thought about this, and I thought, well, maybe we can use something like this. But I knew that it had to be turned inside out because I'm going to be inside the sample, not putting the sample inside the machine. So here's what I came up with. Again, there's a single primary coil. In this case, it's a single turn loop, energized by a current source labeled I in the figure. There's two secondaries, which are wound opposite to each other. So in the absence of a sample, there is zero voltage on the load Z, and the voltage is shown in V. Now, what unbalances the mutual inductance coil set to give you a measurement is the presence of the Earth nearby, because the primary coil will give you a magnetic field which induces a ground current in the somewhat conductive Earth nearby, but that ground current re-radiates magnetic field back into your apparatus, but unequally through the two secondary coils. So there's going to be more flux threading the lower coil than the upper coil, and when you measure the difference, that is directly proportional to the conductivity of the formation. So it's not the magnetic susceptibility anymore, which we are not interested in. That's the in-phase component. We're looking at the quadrature component, which is proportional to the conductivity, the loss, if you will. And that's what gives us our measurement. And this actually, we've sort of built a simple one of these with printed circuit boards, and it actually worked. And I think the next slide is a picture of the lab prototype. So we have on the left, there's sort of a stack of circuit boards, because instead of winding coils laboriously by hand, which I had to do in graduate school, which I truly hated, I printed the coils on printed circuit board material, one-turn loops, much easier, stacked up as I showed you with symmetrical secondary, primary coil, and then, of course, because the thing has to survive these horrible conditions I described earlier, it had to go into metal housing. Now, you're thinking, or you should be thinking, metal housing, oh boy, because metal is about 10 million times more, and literally, I'm not making it up, 10 million times more conductive than a saltwater saturated rock. So you would think that your signal could be drowned by this 10 million X, metal that you're putting nearby. But in fact, the metal acts like a mirror. Skin depth is very shallow. You don't really see a conductive signal from it. You do have to change the positions of the secondaries a bit because it does disturb the primary magnetic field. But basically, if you're very careful adjusting the positions of the three loops, you can get a common mode rejection ratio that's pretty respectable, and then you're all set to go. And the assembled prototype pad is shown in the lower right. Now, this thing was used in the lab to sort of demonstrate that the thing would work. It's an electromagnetically accurate model. It would not survive going into a bathtub, let alone a well, but it did prove the principle. So when we were ready to say, okay, let's try the well, then we had it, really engineered and sturdy, waterproof, all those other good things, high temperature electronics, and we had 4 of these sensors that we put on the 4 arms of this gizmo that we can lower into the well. And the arms are spring-loaded, so they press the 4 sensors into the 4 90-degree spaced azimuths in the well. And so now we've got 4 of those conductivity measurements. So now you might be thinking, okay, you've got 4 measurements, why, and how are you going to measure the slope of the Earth again? So here's the sort of cartoon answer to all those questions. So on the left is a diagram of sort of the Earth simplified, and it's stratified just like you would see in an outcrop, at the surface. But instead of looking at color or texture like the geologists do, we look at electrical conductivity. That's what I can measure. And the electrical conductivity in the Earth varies from about 1 Siemens per meter to 1,000th of a Siemens per meter. So that's a really good dynamic range. So it gives you a lot to measure. So that's a good thing. So let's say that we have these 2 rock layers, one lower one with sigma 1 and the upper one with sigma 2, 2 different conductivities. Now, we've got the 4 sensors. Sensor 1 is pointed to the left, sensor 3 is pointed to the right, sensor 2 pointed toward us, sensor 4 is pointed back into the board. And we're pulling it up at 15 centimeters a second, like our customer is demanding, so we get the heck out of the well. So what happens is that as we pull it up, sensor 1 is the first one to see that there's an interface between sigma 1 and sigma 2, and that's shown in the line plot, the sort of the strip chart recording, you might say, of sensor 1. You can see there's a little displacement from sigma 1 to sigma 2, and then back. Later on, as we pull the thing up further, sensor 3 encounters the same interface, but at the other side of the well. And so that change at the interface is displaced upwards by a known amount, which we measure. And the other 2 are doing the same thing. So I think you can see with pretty simple trigonometry, you can figure out both the slope of that subsurface formation and its azimuth. So what geologists call dip and strike. And in this case, it looks like the rock layers are sort of going up toward the right. And so I would say, driller, drill your next well to the right. That could be north or whatever direction. And you're going to be drilling up dip, closer to the top of your structure, and more likely to find oil and gas. And that actually worked pretty well. It worked very well, in fact. But I told you I was going to figure out which way the wind was blowing 10 million years ago, and I haven't done that yet. So to answer that question, we need to sort of look at present-day landforms. This is what geologists do. And if you go to a desert, you'll find sand dunes, and I put up a picture of a classic dune shape. It's called Barkhan Dune. In this case, the wind is blowing, as you see from the left, that big blue arrow, and horns are sort of forming to the right. So what's happening is that as the wind blows the sand grains from the desert toward the right, the sand grains are sort of going up the backside, the windward side of the dune, and then it gets to the top, and there's kind of a mini avalanche when enough sand builds up at the top. So you get this avalanche down, and then that forms a sort of distinct layer that you can see if you sort of drill a hole into the dune. Then the whole thing eventually might get buried by a volcano or who knows what, and preserved, and that becomes a really great oil reservoir. I mean, there's nothing better than sand dunes, because as you'll see in the next part of the talk, we want grains, big sand grains are good. It gives you a lot of content to store the oil or gas that you're looking for, and also an easy way for it to get out. So now, okay, why do I really care about this? I mean, great, Bob, yeah, okay, it was blowing toward the north 10 million years ago, fine, great. But the importance is that if you drill into this dune field and you do find oil, then I recommend that you either drill upwind or downwind, because dune fields tend to elongate in the direction of the wind. Crosswind, not so much. So, you know, if you drill across the wind, you're probably going to run out of the sand dune field sooner. So it's a better bet to drill in the direction of the wind, either upwind or downwind. So that's how we do that, and that's the importance of it. And like I say, this turned out to be quite a successful instrument that basically paid for my entire lifetime salary. So my employer was pleased. Oops. Okay, so now the bit about corporate jujitsu. So what I just gave you is what I call the Nobel Prize version lecture. Great project, ingenious, worked great, you know, fantastic. But the trip along the way was not quite so pleasant as you might have imagined based on that sort of sugar-coated version of history. This electrical measurement was not the approach initially endorsed by management. They had put all their chips on something different that, frankly, I didn't think would work. So I sort of snuck into the lab on nights and weekends and sort of followed my passion and sort of made this little gizmo, you know, lab prototype, and got it to work, at least crudely, and I had some initial results which looked interesting, and the other project was failing as I predicted it would. So management sort of begrudgingly gave me a technician. Fortunately, he was a very good one. I got some more favorable results, more testing, looked better and better, and one of the theorists in our department asked if he could join the team. I welcomed him with open arms. Meantime, we have an engineering group in Paris. They had their own ideas about how to solve this problem. They wanted to be the heroes. So what I did was I built a copy of their device. I optimized it so it worked better than they got it to work, and I did head-to-head comparisons and showed that mine was superior. So as you can imagine, this was a lot of work, and more than a little interpersonal issues going on here. But the instrument was successful, and it saved our business in the most important oil field of the day, which at the time was the North Sea. Now, when we were done, the technician, the theorist, and I had, as I've written in a memoir, we had time on our hands. how often do you have time on your hands? I don't see a single person shaking their head yes. There's a number of no's here, but I don't see anybody saying yes. Yeah, we're too busy. But while we had time on our hands and we're sort of, okay, what do we do next? We invented something even more important, and that's going to be the subject of the second part of the talk. So part 2, how large are pores in rock 2 miles below the Earth's surface? And why do you want to know that? So, okay, so oil reservoirs, first of all, they are not big lakes. You might get that impression reading Jules Verne novels, but oil reservoirs are actually really just rock that has pore space in it. So you can imagine a sand dune, it's a really good example, riverbed, beach, whatever, sort of sand grains pressed together, somewhat cemented, but with lots of space between the grains. And in fact, a good oil reservoir, gas reservoir, will have 30% of its total volume as pore space, 70% mineral matter. So this is a microscopic view of a good sandstone. It's actually quarried in Kentucky, but it's very similar to oil field rock. And the white are sand grains, quartz mostly. The black are clay particles, which you often find associated with sand. And then the blue is epoxy that was injected into the sample to sort of hold the thing together when the thing was cut into thin section. And so all that blue is pore space that can host water, oil, or gas. Now, the first thing you need to know about this rock is how much pore space. Okay, and that's another story. The second thing you need to know is how fast will fluid flow through it. Now, these grains, you can see, are what, 10 to 100 microns, and the pore spaces are maybe 1 to 100 microns, say. And so the larger the pores, the easier it is for the fluid to flow through. And you can think about the big hose versus the small hose, water hose, but basically knowing the size of the pores is really key for understanding the economic viability of your oil or gas well. So this was a big problem because it's really hard to measure these pore sizes in this range, unless you bring the sample up, and that's slow and expensive. So somebody, not me, but somebody had the idea that, oh, we could use nuclear magnetic resonance for this. Okay, so very quick lesson on nuclear magnetic resonance. So there's a few things you need to do to get this measurement to work. You need a strong constant magnetic field that we call B0. Second thing is you need an oscillating magnetic field that you can pulse on and off, perpendicular to B0, and we call that B1. And then the frequency of that oscillating field has to have a special relationship to the strength of the constant field, B0, and the frequency is given by omega equals gamma B0, where gamma is the gyromagnetic ratio. So that's sort of what you need to do this measurement. It's done routinely in organic chemistry labs. Maybe those of you who have MRIs have been put into that machine. And again, you put the sample into the machine, could be a human being, and there you go. But as you already know, we don't have that luxury because we've got to do it inside out. But I need to tell you one more thing before we get to the apparatus, and that is why this actually gives you pore size. So here is a 4-panel cartoon. This is basically all you need to know about this measurement. So we start with that constant magnetic field B0 in panel 1 pointing vertically, and that aligns the magnetic nuclei in the fluids in the pore space. So it could be oil or water, but they all get aligned with B0. They'll line up like little bar magnets. Now what that pulsed oscillating field does, that B1, is that it tips the spins away from their comfortable, happy equilibrium direction along B0 into the perpendicular plane. And and that's why it's pulsed. You sort of keep the field on until the spins are tipped, and then you turn it off. And that you can figure out how how long you leave it on. That's somewhat trivial. Now, the interesting thing is that now you've turned off the B1 field, and the spin remains perpendicular to B0 even when the molecule that it resides in is moving around. So the molecule can be translating, it can be rotating, whatever you want, but the spin system is decoupled from the motion of the molecule that it's sitting in. So these are nuclear spins, remember. And they will stay that way until they hit a solid surface that might have a magnetic ion like iron or manganese, which is pretty common in sandstone. And then that magnetic interaction at the surface allows the spin to relax in its happy equilibrium directional back along B0, and that's what happens in panel 4. So you can see that if you have large pores, it's going to take a long time for that fluid molecule to diffuse through a surface and allow the relaxation to happen. In a small pore, the fluid molecule gets to a surface a lot faster. So that means that relaxation time is larger in big pores, relaxation time is smaller in small pores. And so, now we have a way of having some notion of how big those pores are and these pores are very small, from micron range, in rock, miles below the Earth's surface. We can't even see the pores. So that's the trick. And now, you probably noticed in that first slide that the pores came in various sizes. And so, okay, how does that work? So at the upper left, I have a cartoon rock. There's 3 sizes of pores. There's the big pore, where it takes the spins maybe 80 milliseconds to relax. There's the medium-sized pores, where it takes maybe 20 milliseconds for spin to find the surface. And then the small pores, 5 milliseconds before the fluids get to a surface. And each one of those populations is characterized by an exponential decay of magnetization. And given an hour talk on this, I could really go into this in detail, but I'm not going to. Just take my word for it. So you have exponential decays with 5 milliseconds, 20 milliseconds, and 80 milliseconds. The measurement is linear. They all add up linearly, so that the total output of the measurement are the black dots, which are the sum of those 3 exponentials. So it's a multi-exponential decay. And the amplitude of each of those decays is proportional to the fraction of pore space of that size. So in other words, if we have, let's see, in this case, 30%, how did I do this? 30% small pores, 30% medium pores, they have the same amplitude. Maybe 40% large pores, it has an amplitude of 0.4. So when you take that multi-exponential decay, do an inverse Fourier transform, you get a spectrum of relaxation times as shown in the lower center plot, with a peak at 5 milliseconds, a peak at 20 milliseconds, and a peak at 80 milliseconds, with the areas under the peaks proportional to the volume associated with that relaxation time. So this is really, really powerful. This is kind of amazingly powerful. You get a volumetrically averaged pore size distribution. So we're in sort of cartoon land here, but let's look at some real data. So here is a real rock, again, quarried rock, similar to an oil field sandstone. The lower axis is that relaxation time, how long it takes the spins to get to the surface in seconds, and you can see it's on a logarithmic scale from 0.01 seconds to 1 second. By a calibration, you can change those relaxation times into what you really want, which is the size of the pore. That's on the upper horizontal axis, and you can see that these pores range from about 0.3 of a micron to about 70 microns for this rock, and that's pretty typical. So you have orders of magnitude range of pore sizes here, and we're able to capture the whole thing. So really powerful. So at this point, I come along and somebody says, okay, Bob, you're so smart, so go build us an inside-out NMR tool. So Well, I had done squid-detected NMR of liquid helium-3 in graduate school, which was like extremely bizarre with superconducting electronics and definitely very crazy. And then at Exxon, I had sort of done more conventional lab NMR materials, and you know, in the big machine that you put the sample inside and so on. So, how hard could it be to build an inside-out NMR? Well, yeah, okay, not obvious, but you know, you've got some time on your hands, so you can think about it. Now again, got to remember the rules of the game. Everything's got to fit into a 4 or 5 inch envelope for an 8-inch borehole. You could put anything inside the tube you want, any kind of magnets or coils. It's up to you, but you know, magnetic fields are pretty unruly, and it's much easier to put things inside them than outside of them because the magnetic fields will spread out very quickly once they get away from the magnet or coil that it's being generated. So, okay, so putting the sample inside the machine is not going to work. So you keep in mind the physics principles that you learned in school: the strong constant magnetic field B0, the oscillating field B1 that's perpendicular to B0, and the frequency. And so that's what you have to focus on, not the picture that you have in your mind of the laboratory equipment. So here's what we came up with. It's something very different than what you find in the laboratory. So on the left is a side view of the whole thing. It's 4¼ meters long. At the bottom section there's see a bulge. That's actually the sensor that we're going to be talking about in a minute, that basically senses NMR in a volume that's about 6 inches long and about a square centimeter in diameter. The rest of it is the power supply, the spectrometer, the telemetry. Everything's got to be going down the well with you because all you've got is that 7-conductor cable, which carries nothing but power and telemetry. So all the electronics you need has to go down into the well, 175 degrees C. So let's look at a cross-section of the sensor region. Again, that's that lowest region on the left. And now, this is the big picture, is the cross-section. This thing is 13 centimeters in diameter, about 5 inches, and fits into the borehole. And so the borehole wall is this heavy black circle, and inside our tube, we have 2 magnets, and they're sort of slabs. They're about 1 foot long each. They are magnetized transversely, so not north-south, but sort of north and south, that way. So you're projecting magnetic field out into the rock in front of you. And again, it's pushed against the borehole wall with the spring system. So that gives you magnetic field out into the formation, which is where it needs to be to make the measurement of the rock formation. So looking at the magnetic field strength, we have, so here we have a contour map of magnetic field strength, and magnetic field is going to be the strongest right in front of the north poles. And then the field sort of goes from north to south, either around the outside or through the inside of this thing. But basically, as you move from top to bottom, the field is strongest in front of the poles, but it's relatively weak in between the magnets. So you have a local minimum of magnetic field strength as you go from top to bottom. As you move out from the face of the instrument out toward infinity, the fields generally fall off. It turns out you have a saddle point in the magnetic field, and that gives you about 1 square centimeter, maybe a couple square centimeters of volume where B0 is relatively constant. That's what you need. You need to have a substantial, some sort of volume where B0 is pretty homogeneous. So that was the condition for B0. Now the B1 is generated by this very strange antenna. It's not a coil, but it's like a coaxial cable. It's sort of sliced in half with the current running down the center conductor, up the outer conductor, and that generates a B1 perpendicular to B0 out there inside the rock, which is where it needs to be. And so that satisfies the second condition. To get the frequency right, that's just getting the electronics. So that's the basic idea, and that also worked pretty well. And it's been used for purposes that I never dreamed of, and no one ever dreamed of. So this is when you know you've done a good job, when whatever you've invented gets used for things that you had no idea what it would be useful for. You don't find that out till later, of course. So, okay, so we're all happy, and then I get a phone call. So this guy calls me up from an oceanographic institute in California, and he says, well, I hear you've got this NMR thing. It can go to remote and hostile environments like oil wells, and we got something that's really tough. We want to send it to the seafloor off Monterey, California, 4,000 meter water depth. So I said, okay, well, what's the temperature and pressure again? He said, well, temperature is 0 degrees C, and at 4,000 meters, pressure is about 6,000 psi. So, I hate to admit this, but I kind of chuckled, and I said, kind of too easy, because we devised an NMR machine that works at 175 degrees C. It turns out NMR does better and better the colder it gets. It really likes to be cold. You get better polarization of the nuclei, and so 0 degrees C sounds great. You know, the machine will operate and we'll get great signal, and that sounds good. 6,000 psi, come on. Our thing is designed for 20,000 psi. This is too easy. Well, it turned out not to be too easy. It was a 3-year escapade to get the thing to work, and here I am. I'm kneeling, installing this thing. You notice the bulbous section that's sort of above my head. That's the sensor section. The electronics is somewhere else. And I'm strapping it onto this remotely operated unmanned submarine that goes down 4,000 meters. Okay, so, and that actually worked out pretty well. So here's the NMR Laboratory. This is the big boat that is the mothership for that submarine, Western Flyer out there in California, and we got several good publications in the Journal of Geophysical Research. So that was fun. And then, you know, now this idea of doing NMR in strange places just kind of takes on a life of its own. And so the next adventure was to the North Slope of Alaska, about 13 miles from the coast of the Arctic Ocean. And here's our drilling rig. We're looking at permafrost. And again, the thing functions in sort of this very bizarre environment where we couldn't possibly take a conventional machine. So, all good fun. So, you know, I've been telling you this story from the sort of my standpoint, the standpoint of an experimentalist who builds gear. But, you know, I just want to make it very clear and that the theorist is an equal partner in this. So the guy that does the theory, solves the equations, runs the computer codes, designs the computer codes and algorithms, is every bit as important, because as you saw, these designs are based on physics principles, and which any physicist can invent. But really the theorist really understands the theory of the measurement, and once there is a model, which is typically a computer model, then you can optimize the design. You can't really optimize the design by building pieces of gear one after another. It's just way too slow and expensive. If you can put it on a computer and look at how the measurement's going to perform in various environments with various different dimensions and with various pieces, then you can optimize it very efficiently, and that's exactly what we did with the help of our theoretical staff. And then, of course, you predict the performance. So this is an example. This is on the lower left is a block diagram of a simulator that simulates the NMR measurement that this instrument performed. It's pretty complicated. It's actually more complicated than this thing would suggest, because the magnetic field at each point in space is different. There's a unique B0 and B1 at each point in space. You have to account for them all individually. You sum them all up, and then you get the sensitivity maps as shown in the lower right, which is where the signal is coming from. Now, in this case, we looked at this and thought, oh, God, this is not so good. because what are those spidery legs that are sort of extending toward the borehole? The borehole is full of water, which has tons of signal generating nuclei. But it turned out that when you take this model and then move it, the spidery legs get washed out. So our theorists said, don't worry about those spidery legs, just start moving the measurement, which we want to do anyway, and they'll go away, and they did. And that was one reason why the measurement worked so well. So it's really a team effort with the theorists being equal members. So just to sum up, there are challenging and interesting problems to be solved in unexpected places. I can tell you that from personal experience. And you may not realize it, but your physics education has provided you with a toolbox of techniques and skills that might prove useful in unexpected ways in the future. And I will say that your experiences will be different, but as I said at the beginning, I adapted to my time and place, and you'll adapt to yours. So with that, I'd just like to acknowledge my coworkers at the University of California who participated in the experiments, and then a partial list of my colleagues at Schlumberger. There are many more, but these are the people who worked on the projects that I described. So with that, thank you very much, and I'll be certainly happy to answer any questions. Yes?
So I'm curious, you're dropping these sensors down, hanging from a cable 10 kilometers down.
Yep.
How are you keeping track of which way the sensors are facing? Because I can't imagine you, with all your magnets and stuff, you can measure the Earth's magnetic field to orient north.
Right. So, okay, there's two different instruments I described. The one that has magnets in it, which would mess up any sort of magnetic measurement of azimuth, it's not actually very important which side of the borehole it's facing. It's going to be on the downside, the lower side of the borehole, because of just the mechanics of the of how it goes down. The one where it's really important, the dip meter application, where you're looking at the slope of the Earth, and you do need to know the orientations of those pads. There is a magnetic compass inside, and it's in a part of the steel housing that's non-magnetic. So that's all taken care of. I mean, that's engineered carefully, and it's common to many, many instruments. So it turns out not to be a problem. Yeah. But it's important to think about it, and we did think about it. Yes. Yeah. You. Well, you were first. Striped shirt. Okay. If you insist, then.
I'm going to ask how advancements in technology have affected your ability to how you work on projects.
Right. Well, I think as time has gone on, there's been much more emphasis on the modeling and theoretical understanding part, because computers have sort of gotten better, the numerical techniques have gotten more sophisticated. So these days, I would say we don't design anything without finite element codes. I mean, we're dealing with media that are very complicated, lossy and dispersive in both acoustic and electrical regimes. And so there's really a premium on the theoretical part, and that has only become more important. Now, recently there's sort of been this buzz about data science and data analytics, and I'm a bit skeptical. I think it's been overhyped, but I think there is something there, and people certainly want to know if there's anything in it for them. So I think you, as prospective graduates, could really help yourself by at least having some familiarity with these more modern methods of data handling, because you will be asked. And as physicists, we are supposed to be innovators. So you'll be expected to innovate and expected to say either yes or no in an honest way, but also have an answer. Yeah?
Well, my question is actually similar, because BP had, a couple years back, BP has the biggest computer farm in Houston,
Yeah.
in the I-10 area.
Yeah.
And it used to be like a year of time to investigate, looking for oil site. Now it's, I think it's 4 years become 1 day old. I don't remember, something like that. And so now there's big data. So many different things happening. The biggest cloud is coming to Houston, from down under. They actually want me to be the cloud architect. That cloud computer is going to be twice as fast as the biggest computer in the world.
Yeah.
And so, what do you expect that we can do that before the big data? I mean, what do you imagine that something that you were not able to do in your time that can be done possibly because of this?
Well, I think you're raising a very good example of what I was talking about, sort of the advance of modeling and analysis. And to take that seismic example, I'm just going to give you a little color to sort of fill out that picture. When you do exploration geophysics with seismic, so that's the sound waves that go inside the earth and reflect off those layers that show the domes, for example, as I showed earlier in the talk, you're collecting an enormous amount of data. I mean, typically 10 terabytes of data to do a seismic survey offshore Gulf of Mexico, not too far from here. And the faster your computers run, and the better your analysis, the more complicated you can make the models to match the data. So there's a real premium on efficient algorithms, principally. Efficient algorithms, and of course, the bigger the computers and the more powerful the computers, then you can run those more powerful algorithms. So I think now you also sort of brought in data analytics into that picture. I think that's probably less important because certainly in the seismic regime, the exploration geophysics area, the processing of that data is very physics oriented. So it very much depends on a acoustic model of the Earth. And if you just took that 10 terabytes of data and stuck it into some sort of AI program, I can assure you, you would get garbage. But so you have to put it through the physics-based algorithms to really get the better images and the more accurate interpretations that we are now able to do with better algorithms and bigger computers. So that's an example where there's no substitute for physics-based thinking and algorithms. But that's a great example.
Could you modulate this technology for any type of material that can be on the Earth, not just for oil?
Yeah. When you talk about subsurface geology, I mean, oil and gas is the biggest sort of single thing. The world produces and consumes 1,000 barrels of oil a second. So it's a very big industry. But certainly similar measurements are made for minerals and so on. Yeah, well, uranium in particular, yeah, because uranium is, of course, radioactive, and we have radioactive sensors. So, and it's not just uranium, but it's also radioactive waste that we've measured, say, at places where they were producing atomic bombs and had a lot of radioactive waste that has gotten into the soil, and that can be measured by instruments similar to these, obviously not the same. These aren't radiation detectors, but we have those. So, yeah. So there are other applications, and the part of the challenge is figuring out, okay, what's out there and what are the needs, and how to match up what's available or what you can invent with a need. Yeah. Yeah.
I guess that partially answered my question. I was going to ask you what because you were solving a very specific problem in this presentation. And I was going to ask you what the other applications of those techniques, like what are other applications of those techniques and how you use them in your work throughout. I mean, aside from, or if you know anyone else who's using this.
Yeah. Well, I'll give you a little bit more detail about that experiment that I was doing in Alaska. So there, the genesis of it is sort of shrouded in the mist of time, but basically what we were looking at was permafrost. And so the kind of mental model of permafrost is that you've got soil that is filled with ice, solid ice. And that's actually not true, because not all the water is frozen even below 0 degrees centigrade. And so a big question is, how much of the water is not frozen, and how fast can it convert from frozen to unfrozen, and so on and so forth. And this is important for sort of geotechnical investigation. So for example, if you're building a structure on permafrost, which people do, it's really, really important to know what the strength of the soils are, and for that you have to know how much of the water is frozen and how much not frozen. So this investigation, using NMR, was able to quantify that. And we related a borehole measurement to a measurement where we actually brought samples up to the surface and measured them both ways with the instrument that I described. And so, that gets looked at by people who are doing civil engineering. That's one example. That's one homey example. The other example that I showed, the seafloor thing, that was an investigation of methane hydrate, which is a fossil fuel, but methane hydrate is really peculiar because it's a form of ice that freezes above 0 degrees centigrade. For those of you who read Cat's Cradle by Kurt Vonnegut, might recognize that scenario. So this is a form of ice that exists above the normal freezing point of water that's filled with natural gas. And so the experiment was, what are the conditions under which it's produced at the seafloor, because it does exist at the seafloor, how fast does it decompose, under what conditions does it decompose, and does that lead to submarine landslides? So one of those articles in the Journal of Geophysical Research talked about the subsea slope failure mechanisms of this very peculiar kind of ice. So, yeah, there's lots of different things you can look at. Yeah.
So this is more about the blip or the orbit you were talking about. How did you feel about how do you see the world seeing a physicist and an engineer? Well, how did you compare them? Because I know the engineers practically suppose they can do almost the same thing as physicists, but I don't know what would be compared to.
I'd say in many cases, certainly for what I'm describing here, they're very, very parallel professions. I mean, they're kind of interchangeable. The theorists that worked, in fact, both theorists that worked on the two projects, they were both electrical engineers who were basically experts in electromagnetic propagation. That's one thing that you get in the electrical engineering curriculum. So it's more of a difference in emphasis. And I'd say for a physicist, a good thing to do is to pick up some of those electrical engineering skills, things like signal processing, which is historically sort of the domain of electrical engineers, but which physicists really have to understand. So in other words, when you get that data, what can you do with it? What are its statistical properties, noise properties, and so on? So I would say they're close enough that it's worth your time to gain some familiarity with what your friends in double E are doing. Still, I mean, physics is a grand profession, and there's neutron stars and gravity waves and so on, so I'm not giving that up. But I'd say that really they're comparable tracks, and you both equally well prepare you for the future. Yeah.
Yeah, this guy in the class. Anyway, I feel like physics, you have to have imagination about what is the different universe, the different worlds we have, but not the future.
Yeah, I think there's a lot about physics that's sort of more fun.
Yeah, because like how do you know there's a gravitational wave, and superfluid is different. So we're in quantum computing class right now. So we're like, okay. I told the student not to study theory because even Feynman is right. So I just wanted to program.
Well, you know, quantum computing is a great area where that's the intersection. You're going to find both double E's and physicists working on it. And happily together, and there's no conflict. And I'd say both courses of study work equally well.
So are you optimistic about it? Because you know the superfluid is different in absolute zero than normal. So they say it's too much noisy. So I've been focusing on quantum optimization and not having too much faith in quantum computing, because I don't think it's going to be precise. But quantum optimization, the more noise, the better. So we're investing on quantum optimization.
Yeah, that's interesting. Well, you know, I'm not really an expert on that, and I'm not going to give you any definitive, you know, authoritative position on that. But I was just at the University of Pittsburgh just last week, where they do have a big quantum computing effort, a good one, a very substantial one. And I asked the same question you're asking. Is there anything to this? And basically, the present state of the art is that it's really a laboratory curiosity. But everything started out as a laboratory curiosity. I mean, as I said, we are the innovators. If it's going to work, we have to make it work. So I don't know whether that quest will work or not, but it sounds like you're looking at an alternate approach, which is a great idea. So without saying yes or no, I'd say, yes, let's work on it because it looks interesting.
What would you say is your most successful achievement in your career as a device? You can settle for a device that you have invented or developed.
Yeah, well,
what would you say would be the most?
Well, beyond doubt, the magnetic resonance, because I showed you how it could be used to measure fluid permeability, which is important. But it turns out it's also really important for characterizing these sort of so-called shale resources where you do fracking. So that's something we never dreamed of. You also use it for measuring viscosity of fluids in porous media, which there's no other way of accessing that. So it turned out to be very, very versatile. And yeah, as far as a piece of hardware, that was my most successful project. Within that project, I sort of strayed away from equipment design, experimental physics, and actually worked out the theory of relaxation of fluids on solid surfaces, which I'd say is probably the single best paper I've written, and one that has probably more citations than anything else I've written. So I sort of ventured into theory myself, and that was a nice little piece of work that took me about 6 months, maybe 12 months, to work all that out. Yeah. So. Yeah.
How did the PhD education help you or prepare you to get into the industry? Because a lot of PhD in physicists go into graduate level research in either school or in a research institution. And you went from that into industry, so how did I use that?
Yeah, well, okay, so one thing is the toolbox. So all the things that you learn in undergraduate, graduate school, that's sort of floating around in your head that you could put together in new ways. So that's one answer to the question. The second answer is that we go to school, especially in physics, to learn how to learn. So I never intend to take another class again. In fact, by the end of my first year of graduate school, I had it with classes. I was just not doing it anymore. I hated the final exams. But on the other hand, I will sit down with a book and read the equations. Okay? So math is a foreign language, but it's a foreign language that I mastered during those years in school. Valuable skill. And then the other thing that you get, if you really take advantage of your graduate school education in particular, you learn how to run a show. That's what PhDs do. So if you're a PhD, get a degree, you will be expected, it is rare for you to be asked to do something routine. You will be asked to innovate, you'll be asked to take leadership, come up with a great idea, put together a team, and make it happen. And even if you don't think you're doing that in graduate school, and I didn't, because my boss was really dictatorial. He ran it, as we said, like a regiment. We all did exactly what he said, but by the time I was done with that, I knew how to do that. And sort of I marshaled my resources and got everybody to work together, and I was not dictatorial. I'm a really nice guy, and everybody who's ever worked for me is still in touch with me. But still, we got it done. So, you know, that's some of the intangibles you get from graduate school. Yeah. And undergraduate is starting to get there. Yes?
So you gave 2 examples of really successful projects that you worked on. Were there projects that just failed miserably, or did you have some successful ideas that the company you work for just didn't really want to work with?
Yeah. Oh God, yes. Of course, I'm not telling you about them. No, okay. So the failures fall into several categories. And that actually is the most important question of the whole session. So thank you for asking it. And I should really make another slide about this. Okay, so why do projects fail, or what prevents you from succeeding? So the easiest case is I got distracted. So I can think of one project in particular where I came up with this really brilliant idea to measure bubble point, which is a thermodynamic property of fluids that's important. And it was really ingenious. And then the guy from the Oceanographic Institute called me up and said, oh, why don't you do this, in a submarine? And the submarine won. And the bubble point project just didn't make it. And that was just due to me not focusing on bubble point. And that's one thing I regret. I had an idea for a gas chromatograph which would have worked superbly well in borehole environment, and never got around to it. And then interesting. Now, okay, so that's one set of things that can happen. This is a rich question, by the way. It really is. Another thing is that you invent something marvelous, it works beautifully, and no market. That's life. I mean, research is taking a risk. And yeah, you got to take a risk. And sometimes you're going to lose, or sometimes the guy in the next town is going to come up with something 5% better, 5% cheaper, and fine, you move on. Hopefully you've learned something, and you can do better on your next project. And the important thing when you knock down is to stand, just like in all phases of life. So, yeah. I mean, there's all sorts of things that can go wrong. You just got to keep at it. Just go back. So, it's a good point. These projects came after other projects that failed. That's really an important point. Yeah?
So any possibility that helium-3 maybe find more?
No.
No?
Absolutely not.
Any possibility that superconducting white body oil gas?
No. Okay, let me tell you something about helium. So helium is a rare gas on Earth because it gets into the atmosphere and promptly escapes into outer space. Helium-3 is even more rare because natural abundance is about 10 to the minus 6. So helium, normal helium, 2 protons, 2 neutrons, is the main product of thermonuclear reactions in stars. So the universe has a fair bit of helium in it. Earth not so much because it gets away. Helium-3 is a very unusual reaction product of the synthesis of elements. And in fact, the helium-3 that we used in the lab, and that you'll find in any lab today, is actually a decay product of tritium, which is produced artificially for the purpose of making thermonuclear bombs. So if there was no thermonuclear bombs, we never would have done helium-3 research because we couldn't have found enough helium to do it. So we're actually using decayed bomb material to do these experiments. So this is exotic. Now, we're physicists. We're really curious about helium-3, but there's not much of it in naturally occurring. There really isn't. So, no practical application whatsoever. I mean, in a way, I was very naive. I always thought I was going to go to graduate school and study helium, which was really interesting in the textbooks, and I wanted to learn more about it. And I really didn't think further than that. And I was naive. But on the other hand, I had a good education. And I bet there's a lot of people in this room who match that description exactly. All the neutron star people, by the way, match that description. And good for you. It's a good education.
Any questions?
You all exhausted?
Do you ever get weird calls from people who have taken your inventions and put them somewhere weird and call you up and ask for consultation or like troubleshooting?
Yeah. Oh, yeah. Well, aside from the submarine, yeah, so I got a call from a company that made rocket engines. This was a strange one. So for solid fuel rocket engines, the fuel has to be very uniform. And they wanted to know whether my thing could map non-uniformities of fuel inside the engine. And if the rocket fuel is not inside of a metal casing, yeah, it would be hard, but maybe feasible. But in the end, we decided no, it had to be in a metal casing. So things like that do come up, yeah. Yeah. But if you have any strange suggestions, I mean, if you have to. Not yet. Think about it. Okay. Good. Good enough.
All right, let's thank our speakers.
Okay. Thank you.
And I want to remind everybody that James Burke is going to be here from NASA next week talking about orbital debris research. So
That sounds fun.
Make it by. And for the students who are taking either 6838 or the undergraduate 4372, please make sure I get the write-ups next week. Can you come?
Let me stop recording on this thing. Okay.